Thank you, and thanks everyone for coming out. I'm here today to tell you a story of how we sort of had an observability gap at a really important time during the year for us. So show of hands, who has to deal with transient network failures from time to time? And how many of you feel like it was an easy task to diagnose those transient network errors? Yeah, it's a tough problem. So I work at Shopify. My name's Jason. Shopify is a commerce platform. I work out of the lovely city of Ottawa, the capital of Canada. I've been there for 4.5 years, and I've seen a lot of growth over those years. And with growth comes challenge, and one of those challenges is traffic. So to quantify that, we deal with approximately 83,000 requests on average per second. But it can peak at a little over double of that, 170,000. So there's lots of traffic. Lots of traffic means those once-in-a-blue moon issues become a little more common. And one of those issues is connecting with an upstream. So we deal with that. We have resiliency primitives. Acton called out this morning, one of the advanced sort of things we have in our toolbox is circuit breakers. So for those who aren't familiar, circuit breaker is basically a primitive that lets you fail fast when an upstream is failing. Basically, the idea is if an upstream is failing now, it's probably going to fail again. And it helps sort of take some pressure off that upstream. So we're primarily a Ruby shop, and we built the Simian Ruby library to make it really easy for all of our developers to take advantage of these resiliency primitives. So just shy of a year ago, early October 2018, we were observing lots of open circuit breaker errors. Specifically, yeah, kind of looked a little bit like this. So everything was kind of on fire when we were trying to connect to our Redis cluster. But it was only happening during flash sales. So what's a flash sale? It's basically sort of almost the bread and butter of our platform, where basically there's like a limited inventory sale or just a short sort of time span where they're giving away an item, and just everybody, bots included, just bombard the system to try to get those items. So it's short-lived, transient, maybe a little less transient than some things you may deal with from day to day, but everything was on fire. And we didn't really have a good signal at what the problem could be. To add urgency to the issue, this was near Black Friday, Cyber Monday, which is a really big season for us. And if you're not familiar, Black Friday is the day after American Thanksgiving, and it's a huge time for sales. So yeah, and a large number of our customers are American merchants. So this is a big deal for us, big deal for our merchants. So availability, very important. And last year, sort of $10 billion was spent for Thanksgiving and Black Friday online. And this is just for online. I'm not even including the retail stores. And know that these numbers aren't for Shopify. This is all online. If we assume a 25% increase, which is what happened last year, then this year we can expect 12.4 billion. So it's really big. So we started looking at the graphs from earlier. We're like, OK, cool, high CPU load. Let's dig into that. So we found a node that was experiencing some CPU issues. Pulled out the good old perf from the toolbox, which you can find pretty much with any modern Linux. If you're not familiar, perf just sort of samples events, for example, call graphs or CPU stack traces. So we took this profile from perf, ran it through Brendan Gregg's sort of flame graph tool, got this. What's interesting are the long bars. Those are where most of your samples that you found went through. So specifically for us, we found, oh, cool, connection management, network problems. Seems reasonable. So we were like, great, we found it. Let's dig into it. So we actually patched Redis, which is scary going into Black Friday, Cyber Monday for a commerce platform. And it helped, but it didn't fully resolve our issues. So we had to keep digging. So we had another engineer observing some elevated TCP retransmits. So before I get to Network Monitor, and before I even worked on Network Monitor, I didn't actually have a lot of knowledge about TCP. So I actually want to dig into that a little bit, for those in the audience that also aren't super familiar with how TCP works under the hood. So here's the TCP portion of the packet. A lot of stuff happening. Let's just look at a couple of important parts. There's the source and destination port. If you're asking where's the IP address, there's another part of the packet that has that. It's the IP portion of the packet. There's the sequence number. The sequence number allows you to sort of order things and get reliability. It's basically a monotonically increasing number. And you could implement this on top of something like UDP if you really wanted to, but it's all there for you in TCP, which is great. Also for reliability, we have the acknowledgement number. And this is basically when the receiver of a packet wants to acknowledge a packet, they send back basically 1 plus that sequence number, saying, hey, this is what I've got. And that lets the sender know, hey, this is what the receiver got, and you have that reliable communication. So to establish a connection, we first send what's called a synchronized packet. Basically, typically you choose a random number, send that along. The server then acknowledges the number plus 1 in that acknowledgement number, but it also sends its own sort of randomly chosen sequence, which then the client acknowledges, and now they both know each other's sort of sequence number that they're working with, and you have that bidirectional communication. So we call that the three-way handshake. Now great, so you have a connection, so let's send some data. So you send some different packets. They're all numbered 1, 2. These are the sequence numbers. The receiver is like, acknowledge 1, but something happens, and for some reason, the acknowledgement of the second packet doesn't get to the sender. So what happens then? What is a reliable transport? So we have this thing called a retransmission timer. When that fires, it'll retransmit the packets that haven't been acknowledged. And we have a lot of optimizations. By we, I mean the general we. I have a lot of optimizations to make this a little more efficient over the years. For example, selective acknowledgements mean we only send, if we see acknowledgement, let's say for packet 5 here, then we know we only have to send 2, 3, 4. So just a lot of optimizations. So that's how we get reliability in TCP. So we were seeing these TCP retransmits, and they trigger during normal operation. So if you see one of these, there's no reason to freak out. Maybe the network's congested, or a router could be busy, and packets just end up getting dropped. Firewall rules. Sometimes you just drop the packets, no acknowledgements go back. Or maybe, just maybe, if you're really lucky, a shark comes and bites your underwater cable in half. But regardless of why, we're really concerned when there's a lot of retransmits. And that's exactly what we saw. So we investigated very deeply, and in the end we realized there's something outside of our observability, outside of our observable universe, and we weren't quite sure what it was. So we did our due diligence and sort of engaged our cloud provider and said, hey, can you help us out? They got some network engineers, came in, found an issue, and were able to help us diagnose this. But it was something that was outside of what we could actually observe. So knowing that, we're like, we don't want to be in this same hole again in the future. So just to give some perspective, that took 6 weeks, and that's not just one engineer. Many engineers were pulled in to try to take care of this issue because of that urgency of Black Friday, Cyber Monday. So we were inspired by Microsoft's ping mesh paper. So ping mesh was just basically a way of creating a complete graph between a bunch of nodes and just regularly pinging them to get some baseline latency measurements. We thought, cool, that's interesting. This seems like a good place to start. So instead of just starting off building our own, we did seek out some existing technology. The only one we found, which was, I love the name, Bloomberg had a project called Goldpinger. And for anyone that likes James Bond, great name. So we added, it kind of had this visualization on the left. It's pretty hard to notice patterns in that. So the ping mesh paper had this great grid visualization. So whenever you have this sort of graph, or especially a complete graph, very useful for visualizing and just quickly identifying patterns that exist in your data. But in the end, we decided, okay, it's a little too challenging to take Goldpinger and adapt it to our needs. So we just rolled out really quickly our own ping mesh, and we had to integrate this into a multi-cluster setup with some internal services to help us build it out. So what was really interesting, though, too, is when we were timing our own latencies and how long it took to establish connections, the data was kind of noisy. It wasn't really reliable. In particular, we found that user space is not great for timing any sort of short, fast kind of event, like a connection establishment, maybe something else. But we were getting hit by two things. Basically, Go routine scheduling. You know, a Go routine or a thread gets put in the background, and now you're also including idle time. And for something that takes several seconds, that's probably, you can ignore it. But when when you're measuring something that's on the level of like microseconds or like low milliseconds, like it can add up very quickly. We also got hit by C groups throttling because we're in Kubernetes. So it was very sort of bursty, and we got throttled a lot. And one way we could actually deal with that is okay, Kubernetes, give us everything you got. But that's not really good for like a lightweight observability daemon. If your observability costs more than your actual everything else, then probably you want to rethink what you're doing. It's also another problem too, right? If you have high resources, maybe your daemon doesn't actually even get scheduled on a bunch of your nodes. So now, again, you still possibly have an observability gap. So we're like, how can we deal with this? So a colleague told me about eBPF. So I started exploring that. So what's eBPF? It's called Extended Berkeley Packet Filters. And you can find it in the VM in pretty much any modern Linux kernel. It also has a JIT to sort of take this BPF bytecode that runs in the VM and compile it to some fast native code. It runs the programs that you put into the VM can be attached to various events. So for example, let's say if you wanted to trace whenever a function in the kernel is being called, you can attach what's called a kprobe. Because it's running in kernel space, it's pretty important that these programs are safe. So there's a lot of restrictions and verifications done for safety and correctness. You can't loop, at least not infinitely. A bounded loop could work. Memory access is bounded, type checked. It checks for like null dereferences. Programs are pretty small, 4,096 instructions, at least by default. I think you can configure that if you want to build your own kernels. But you can chain a bunch of these programs together to sort of overcome that if you really need to. The maps allow you to sort of communicate out. It's your only way of communicating with user space. So you basically put things into a map, kind of like a hash table, and user space can then read from those maps. And there's also some really interesting modes. For example, Express Data Path. It allows you to attach programs to network interface drivers, and you can actually process packets as they're coming in. So an example of some tech that's being built on the Express Data Path, I think, is BPF Filter. It's a replacement potentially for IP tables or NF tables. So some really cool technology. You can do some really powerful things here, and it's really highly customizable because you can attach and reattach these things all fairly frequently. So I just wanted to also quickly dive into what a BPF program looks like. For anyone that's not a fan of C, don't worry, it's not too bad to follow this. Let's dive in though. At the top, we sort of create our BPF maps using the BPF hash macro. So we have two maps in this example. The first map called data. This is going to be our map that the user space would read from. And what it's going to do is it's going to map a destination address that we're connecting to. We're going to pack that into a 32-bit integer. And it's going to map it to the time it took to establish the connection. And you can map much more complex keys than a U32. You can pretty much put any struct in there. The second is going to be the start time. So when we have a socket, before we even send that very first synchronized packet, what we're going to track is the time that right before sort of that SYN packet was started. Next, we're going to have our first kprobe. We're going to connect it to the TCP v4 connect. And this is a function in the Linux kernel. So you do have to dig around in kernel code, which I found a little intimidating at first, but very enlightening and intriguing after. And TCP v4 connect is any IPv4 connection, we'll call this function. So what we do is we just sort of get the current time with a BPF function, and we put it into this start map. Next, we have our second probe, and these fire separately, and this is why we need the start map. And our second probe kprobe is going to be on TCP finish connect, and this gets called pretty much to complete any TCP connection. We start off with some sort of sanity checks. Is the socket null? Is it in the right state? If we are finishing our connection, then it should be SYN send. Anything else would be not a good state to be in. We look up in our start map, are we actually tracking the starting time for this socket? If not, bail out. And then finally, if all of those conditions are met, we get the current time, subtract off the start time, I even divided by 1,000 to put it into microseconds. Put that into our data map, and now user space can read that data. And we delete it from the socket from the start map, just some janitorial work to clean up after ourselves. Maps do have a finite size, and BPF will make sure that you don't exceed that. So memory is, you can't run out of memory from one of these programs. So it's useful, but it's nice to clean up after yourself. So there you have it. That's a quick little program to actually create to track TCP connection latency. And if you notice, yeah, that's C. That's not bytecode I'm writing. There's a project organization on GitHub called IOvisor, and they have a lot of really useful stuff for interacting with BPF. One of those is BCC, which is the BPF compiler collection, and that's what you can use to actually compile that sort of C-like code into BPF bytecode. And there are bindings in other languages. Like, for example, when we built Network Monitor, it was in Go, and there's a Go BPF library that you can use where you can feed it one of these programs and attach it very easily. There's also a lot of really good example programs and tools that just come with the BCC repo. So I encourage you to check out, if you're interested, check out the IOvisor project and look through their examples and see some of the stuff that they do. So how did that resolve our problems? Well, now that we're in kernel space, no cgroup throttling, no Go routine scheduling problems. When one of these BPF programs run, the kernel actually disables preemption. So it's going to run to completion. So what you get is a really smooth, sort of reliable metric that you can potentially alert on. So for example, here we have my two user space and kernel space via BPF metrics. And this is the max value for the metric over a period of time. And the user space is just too noisy and too high of a variance to make it really useful to sort of trigger on. You can also see that the top yellow line, it's just the average value of that is just way above the true value of what's actually happening. So this really helped us. So now that we understood BPF, we sort of built out a multi-cluster sort of setup. We have a daemon set. Again, like I said, we're running in Kubernetes. The daemon set will ensure that our BPF programs of metrics that we want to track are attached on the nodes. We also have some things running in the background that make sure they get cleaned up. The daemon also is responsible for tagging these metrics, or collecting them from the maps and exporting them, but also tagging them with really interesting metadata, like the container names of the source and destinations of our communication. We set up our inter and intra-cluster ping mesh, and we have a federated Prometheus cluster to collect all these metrics and bring it all into one place so that we can sort of aggregate and look at the entirety of the data set. So now we have that done. We have a great way to actually run any of these BPF programs. We also exported all of our data to Datadog, which is what we primarily use for monitoring and alerting. And we actually, because of the scale of our company, we actually encourage all developers to operate their own services. So by putting it into Datadog, which is what everybody's using, they can now sort of correlate and identify network issues that maybe exist in their namespace and compare it to sort of regional baselines. So now we filled that observability gap. And I've heard from many other production engineers that this has actually been really valuable for correlating other negative events or engaging with our cloud provider. It doesn't always tell us exactly why or what's happening, but it helps isolate sort of where things could be going wrong. And we probably still have blind spots ourselves. Just like this dog missed a couple of windows, we probably missed some things too. But at least we have this great platform that we can build upon. So that's our story, where we recognize that there's a layer where we were missing some observability. So I'm hoping, well, like myself, I didn't know TCP, so maybe you've learned a little extra about TCP. You have now a new technology that you can explore, where you can get, for short-lived events that happen sort of at a low layer, you can sort of get great, stable sort of metrics there. And specifically, why running sometimes in kernel space is a useful thing. And finally, I want you to walk away thinking about, okay, maybe my company has some blind spots. Maybe we're not really observing there. And yeah, I don't want you to end up in the same situation where several engineers spend 6 weeks trying to debug an issue before a critical time. So thinking about those, it would be a really useful thing to do. If anyone saw my profile, I'm a cat person, so here's my cat. But thanks for listening.